Okay, hello, welcome back. Hope everybody's doing well. Today obviously is the last lecture before we go off on our holiday break. I'm sure you all are looking forward to having a little rest, as am I. Today's lecture, we're going to pick up, of course, where we left off last time. We're going to finish these closed cell, open cell, and stringer web, today's stringer web sections, where we look at reinforced cells. And, these are all really critical aerostructures. These are the structures that you're seeing in your wing, the structure you're seeing in your fuselage. Many structures around aerospace are all composed of these things. So understanding these and knowing these well is a great goal for you guys as students. After that, we're actually going to transition into the next part of the course. If you recall, I sort of loosely described this course as having three parts. And the first part was the elasticity portion of the class. That was very fundamental, of course, and it's been used continuously as we have moved forward throughout the course. Then we moved into the engineering solution portions of the course, and that's really beam theory, and we've been now in beam theory for many weeks. We've addressed bending, we've addressed torsion, torsion of solid sections, torsion of thin-walled sections, open and closed. But then last but not least, we're going to move into the approximate solutions method of the portions of the course. That's the energy methods portion of the course. And so that's what's coming up later today. Let me go ahead and fire up my presentation mode for you. Okay, so picking up this new concept, just to remind you what happened last time is we finished up closed cell sections. So closed cells we had initially drawn, we started with something like a circular thin-walled beam structure that was carrying a torsion load. And the next and last thing that we did then was multi-celled structures. So the classic example is probably the airfoil structure. That then is divided, has a leading edge and a trailing edge spar. So now we have three cells. And so we talked about how to do those, and we did closed cells and open cells. Now the last thing we're going to look at is reinforced structures. So those thin-walled structures, turns out thin-walled structures actually suffer from a real tendency to buckle. And so we need to reinforce them. And by reinforcing them, we actually create a set of load-bearing members that are, in some sense, idealized and optimal for the task that they are meant to accomplish. Okay, as you can probably see here on your screens, this now represents a reinforced structure. Now, the image itself, I think perhaps lacks a little clarity, so I'll just for the moment add something to it. So again, this is a beam, right? It goes off into the distance. So this is off into the z-axis. We're looking at a two-dimensional cross-section. I'll highlight that two-dimensional cross-section here for you. Okay, it looks something like that. And what is shown here in the diagram, it's hard to see because it's more of a schematic than it is actually a diagram, is now reinforcements that are on this thin-walled structure. So thin-walled structures tend to buckle. We don't really want them to buckle, and so we'll often reinforce them. So here we have an area A, A1. Here's another area A2, area A3, and A4. So what you're seeing is not only do we have a thin-walled structure, but at points within the cross-section, we have a reinforcement. So it's rare that these would actually be circular cross-sections that then extend off into the z direction. Rather, it may be something that is more like an I-beam, or maybe even like a C-channel or something like that, where now it's a really thickened portion of the spar, something like you're seeing here rather than this. But this is an idealized, easy to calculate first entry into this concept, which allows us some relatively straightforward and simple calculations. So if you remember our discussions from the past several lectures, we know that shear flow is related to axial stress. in fact, we derive this equation up here. That is that the derivative of the shear flow with respect to the S coordinate system is equal to minus the thickness times d sigma zz dz, the derivative of sigma zz with respect to z. Okay, so this is more of a bending stress over here, sigma zz. Its derivative then leads to this shear that's present in the structure, and that's ultimately because shear and bending are related, not the same, but related, and that's how this equation came about. And then we had taken this equation and we plugged in our known values for beam bending stresses, and that led us to this version of the equation, which at this point seems rather lengthy, but you've seen it, you actually saw that it's fairly easy to understand once you kind of get the hang of it. And often it's, in fact, really quite easy, especially when you have symmetries in the problem. So if we had a symmetry, we don't necessarily know that we do because we don't know the values of A1, 2, and 3, and 4 are, but you can imagine there might be some symmetries, for example, about the x-axis in this problem. And then IXY goes away and life gets easier here. Okay, so that's the big summary that takes us to the key point. Again, what we're doing is we're making assumptions along the way. That's what these engineering solutions are. We recognize elasticity is just a little bit too hard for many of the problems, if not most or all of the problems that are real-world engineering problems. Straight elasticity, very difficult. And so if we can make some geometric or material observations that simplify the scenarios, then that's great. And that's what we're going to do. So what do we see here? We see these equations. So we have shear flow that's related to bending. Okay. Now, keep in mind that, well, a couple things. So the integrations themselves are related to the first moment of the area measured from the centroid. So, right, these are centroidal-based integrations. And also recall another thing. That is that an integration is nothing more than a sum. It happens to be a sum of a number of small pieces. In fact, we take differential pieces, an infinite number of differential pieces, and add them up. But, an integration, nothing more than a sum. So now, so that's just a reminder to you. Now, the next statement, let me go back to this image for a minute. Okay, again, what do we have? We have these reinforced structures. So we've got big concentrated areas here. And then we have thin-walled structures. Okay, keep in mind that thin-walled structures tend to buckle. They can't carry compressive load very well, for one thing. And so and that's part of the reason why we reinforce these. And so what we're then going to assume is if it was carrying any compressive load on the bottom side, in the sort of the thin-walled portion, that would likely buckle, and that compressive load would functionally go away and be carried by something that was more rigid. And we can make a similar argument at the top. Well, if we're not carrying any compressive load in the thin-walled section on the bottom, then are we really carrying much of a tensile load in the thin-walled section at the top? And, actually you could make an argument that it's possible for that thin-walled membranous type material to carry load. But you can also look at this and say, well, the vast majority of the area that's present here is actually concentrated in these reinforcements. And so let's make the statement that, yeah, we're going to assume for the sake of argument that the thin-walled portion of this structure is not carrying any bending load. Okay, so the bending load is carried by this big structural reinforcements and not carried by the thin-walled structure. Okay, so that is an assumption we will make. We will make this assumption that the stringers carry all the bending load. Now, consequently, what do we learn? If we've made that assumption, then in what we're calling the web section, this is the thin-walled portion of the structure, in that section we are assuming that sigma zz is small. It's negligible. In fact, we'll go so far as to say it's 0. Now, when that is the case, of course, we can plug that into this equation here. dq ds is now equal to minus t d sigma dz, but if sigma is 0, then this right-hand side, again, becomes 0. So what does that tell us? If the right-hand side is 0, dq ds is equal to 0, we make the conclusion that if these assumptions hold, and they actually turn out to be reasonably good assumptions, if those assumptions hold, then when we integrate this equation, we get that q is equal to some constant value. And we've made that argument before. We made it for different reasons previously, you know, slightly tangentially when we were doing the torsion problem, right? We had the 2 arrows representing torsion coming out of our shaft. We said, okay, we're going to treat this as a torsion-only problem. We'll solve the bending problem separately, and we'll add them together. So that was the case of assuming the bending stresses were 0. Now we're assuming the bending stresses are 0 for a slightly different reason, but we draw the same conclusion, that in these regions, the shear flow is constant. Now, are there any questions about that before I move forward?
I have a question. So how much larger does the area have to be in comparison to the web for this assumption to work? Is there like a golden ratio, well, not golden ratio, a rule of thumb ratio, like for the previous ones?
Was that David? I'm not seeing faces right
David.
now. I'm going to quickly see if I can switch my configuration to show faces. Hold on just one second. Turn on captions, change layout. We'll see if somehow I switched it to spotlight. I don't want to spotlight myself. I'd rather see you guys. Okay, there we go. Okay, so great question, David. Just to reiterate what he asked, he said, well, how thin does this need to be negligible? Or, you know, sort of similarly, how big do those areas need to be? Obviously, recognizing that it is some sort of ratio. And, you know, it's a great question. It's kind of a rule, you know, is there a rule of thumb? I would say most of the time with aero structures, we're going to have skins on the wing or skins on the fuselage that are going to be relatively thin. And the principal load-carrying members, so this would be the spars in the wing or the longerons in the fuselage, either of those, given the need to carry substantial bending loads, those are generally going to be quite thick in comparison, big and bulky in comparison to the skins. And so for most aero structures like that, this is a reasonable assumption. Now, that's not exactly the rule of thumb that you asked for, but it's more of a, you know, I don't want to say fundamental, but it's quite a pragmatic approach. Now, the other sort of as yet unasked question is, well, what is the consequence of making that assumption, right? So this is related to your question, David. You know, if it's not exactly thin, well, what is the consequence? If it's not infinitesimally thin, what's the consequence? And then, you know, okay, so it has some finite thickness now, so what's the consequence? So the consequence is this. If the skins actually contribute a little bit to the bending load, well, then what happens is, yeah, it's true, the shear flows are not necessarily constant anymore. However, the bending loads carried by the principal bending load-carrying members then decreases. And so you sort of get this circumstance where making these assumptions, when you assume that all the load is carried by one, it's kind of the worst case scenario for the bending load carrying members. But you know, any amount of load that would be carried by the thin-walled members would decrease the stresses in the principal load carrying members. So it's a conservative approach. And sort of vice versa, the other way also sort of applies. We're going to assume in the future that the principal bending members don't carry any torsional load, And of course, we recognize that ultimately they will carry a little bit. And so what does that mean? That means that the principal torsion carrying members, these are the shear webs and the closed cells, they actually carry less torque than what our theories would assume. So in both of these cases, we end up with a conservative assumption on the amount of stress that's calculated given the loads that are present. So that's not quite as clear a rule of thumb as I gave you with, you know, the length to width ratio and some of those other ratios we've used along the way. But I think it's quite a pragmatic way of thinking about it. Does that answer the question, David?
Yeah, thank you.
You're welcome. Okay, so anyway, Q is constant. Now, Q is constant only where the shear, or where I should say the bending loads are assumed to be zero. Now, when we're crossing, let me go back to my image here for a moment. So if we're assuming that, I'll draw it bigger actually. Let me go to this slide and I'll just draw big. Okay, so here's the scenario that we've laid out for ourselves. Okay, now we can define a coordinate system, say S in this direction, and we can say here at this point, you know, like we've done in the past, that the shear flow here is zero. Right now, we just said, well, the shear flow is constant, so one might think, well, that means it's going to be zero from here over to here, and then from here down to here, and from here down to here, and that doesn't make any sense, and I would agree with you completely. So what we need to recognize is that when we have this arrangement that we have, we can still define our shear flow or our S coordinate system at that location, but we have this load carrying member, this bending load carrying member that's present, this structural reinforcement. So as we move from the shear free, traction free side to the inside, since this member is actually carrying stress, that member, it's in that reinforcement, the shear flow is not considered to be a constant anymore. That's actually dependent on the load that's being carried. You know, go back to our equation. So for this small region right here, as we go across that region, we see that we're going to have to end up with a delta Q that occurs as we go across that region, because for that region, we have a non-zero sigma ZZ. Okay, now that leads us to the, oops, let's see here. Where was I? Right here. So that means that we start here with Q equals 0. We get a delta Q here. Then we have a constant value of that through this section, Q, and then we get another delta Q, and then of course down here we're going to get another delta Q, and then over here we're going to get another delta Q. And of course one might sort of by inspection recognize that by the time we get to this side over here, we have to get back to the Q is equal to 0 scenario. Okay, so the next thing we can look at is how does that shear flow change? And here's the equations for that. So the change in shear flow that occurs over that stringer section, this stringer section that carries bending load, is determined by examining the integral. That integral ultimately comes from, where was it? This one here. Actually, really both of these two. So this integral, the integral of from 0 to s of x t of s ds, you need to think about what that represents. Well, the thickness times ds, so you can almost think of that as being, that's this portion right here. This is, you know, functionally equal to dA. Right? It's a differential area. It's a thickness times a differential length. So that is ultimately a differential area. And so we're doing an area integral. But then we also recognize that the integral, the shear flow magnitudes are constant from point to point. So this ends up being a sum over the number of stringer reinforcements that is 1 to I reinforcements, of the position of that reinforcement times its area. So, summary, an integral is a sum. In this case, it's a sum of a differential area. And what we're doing is we're recognizing that that differential area, since for this particular differential area, it's all essentially located at the same x. Let me go back to my drawing. So for this large area, it is functionally, pretty close to all being at the same x location. So this is basically saying, all right, I'm going to sum up of that x location times the area. And in C.T. Sun's textbook, he calls this magnitude Q, capital Q. And again, you can think of that as a shear magnitude now. Shear flow times a length gives us a shear magnitude. So this is, a delta across that region. So I think I've made this clear already. AK is the area of the stringer section K, where K varies from 1 to I as we're going around. In this case, this would be number 1 here, 2 here, 3 here, and 4 here. Okay. So, and of course, in this location, X and Y are the distances from the centroid to the stringer area. It's really the centroid to the centroid. So it's the centroidal location of the whole thing, which we're going to say is right about here, to the centroidal location of that area. So in the end, what we get is what I like to think of as step changes in the shear flow. It goes from 0 to some finite magnitude, then it becomes constant, then it goes to another finite magnitude, it becomes constant, and so on. Okay, is everybody with me? I'm going to go ahead and do an example if you guys are ready for it. So I'm going to do this calculation for this simple cross-section. We're going to say it's a C channel, a load carrying member. It's a beam. It's carrying bending load. Okay, it has four reinforcements that ultimately have areas associated with them. And I'm going to say that area 1 is going to be equal in size to area 4. Area 2 is going to be equal in size to area 3. So this gives us some symmetry about this x-axis that I alluded to earlier as making the problems quite easy. Okay, there's actually no reason that we have to do that. It just makes the sort of lecture examples easier. Okay, so the shear flow Q produced by a vertical shear force. So I'm going to make this assumption that here we're going to have a shear force SY that goes through the centroid. That is going to be equal to Q times minus SY QI over IZ, where QI is equal to the sum as we're going around that domain up to the point where we are. Okay, now I want you to recognize that this equation, take a mental picture of that equation right now. It is minus SY over I times this Q value. That Q value resulted from the integral. Here was that integral. So we got rid of SX because it was, we assumed it wasn't present. We got rid of IXY due to symmetry. So this this whole term goes away, boom, right? And then what's left is this term. So we have SY, IXY goes away, IXY goes away, cancel here. So we have minus SY over I times this integral. And then just a few minutes ago, we showed that that integral was equal to this value, which is now represented here as Q. So it's the same integral, it's just now represented in this way. It's a more discrete calculation. And note that I got to want you to notice here, I have IZ because this is what CT Sun has in his textbook for this example. But, in our case, we probably want to think of that as IX. Okay. Anyway, so this is Q. Now, the next thing we need to do, of course, is one of the things we need to do is calculate the area moment of inertia. Now, if we go to this cross section, you might think to yourself, well, that actually can be a little tedious, but I'm going to make the argument that it's actually fairly easy. So we're making this assumption that the bending is all carried by the concentrated areas, and we can extend that assumption to say that the value of the area moment of inertia really should only include the portions that are carrying that bending load. So we're going to neglect the thin-walled stuff for the purpose of calculating our area moment of inertia. So here, I'm just going to say, and in this case, we're using parallel axis theorem. So Ix is going to be 2h squared times the sum of the two areas. In this case, you'll note that h is the distance from the centroid vertically. The total thickness here is 2h, and so I'm counting h as only one distance. And of course, you guys remember the parallel axis theorem. It is the local I value, area moment of inertia of the local section, plus the distance squared times the area. And so in this case, we have the 2 comes from the fact that it's symmetric up and down. The A comes from the areas, and the h squared comes from the distance squared. And we're doing two things here. We're neglecting the local I value because it's going to be small relative to this magnitude. So all of these assumptions we're making in this calculation of I are also conservative, because the lower this value is, the higher the stress calculated stress is. So when we neglect small contributions, we're getting close, but we're on the conservative side of the calculation. Okay, so again, we're working our way around. Now I'm just going to go ahead and draw this one more time. I feel like I got to draw this stuff a bunch of times. It's just, I should put the same image on every slide. Okay, so we're trying to understand what's the shear flow, for example, in this region here. We start our S-coordinate system over here going inwards, and we start counting I's. So, out here there's no shear flow, it's traction free. We step through that first segment. We have now a constant shear flow that I'm going to call Q1. And Q1 is the sum of all of those flows, right? So here it's the sum, in this case from 1 to 1 of Y1A1. So this magnitude of Q is simply going to be Y1A1, and we're substituting in H for the value of Y1. So Q1 is simply A1 times H. So the shear flow is going to be this over the I value times the magnitude S. And so, here, pretty straightforward. Here's our shear flow in that section. Of course, it's a good idea to simplify when you can. So, if I simplify that equation, it becomes this. Q1 is equal to minus SY A1 over 2H A1 plus A2. The next thing we can do is we can calculate Q2. Okay, Q2 is this shear flow here. So we had a magnitude of shear flow as we got to this second concentrated area. We're going to jump over that area. We're going to add to that calculation for shear flow. Because what we're doing is we're summing from I now, I being equal to 1 to 2. So it becomes Y1A1 plus Y2A2. That's what Q2 is going to be. And therefore, this is what we get. SYH A1 plus A2, because the Y's were the same and now the areas are different. But this was Q. This, of course, was still I, and we can still simplify that. And so therefore Q2 is equal to minus SY over 2H. And it's going to be relatively constant for the reasons we've already argued. Now, last but not least, of course, we can do Q3. I'm going to take the magnitude here, which is the same for this entire vertical portion. We're going to jump over this next section. We're going to add yet another AI times YI. Okay, and that gives us, because the A values are different, so we get A1, A2 minus A2. Actually, we're jumping over an area that is A2. It becomes minus because it's now in the minus Y direction. And so lo and behold, you simplify that and you get it down to this, which of course what we saw was in magnitude equal to Q1. Okay, so now we have the shear flows in each of these three locations. We have it here, we have it here, and we have it here. Note, in each case, it had a minus sign in front of it. That means that, I drew my arrow in from this orientation or this origin leftwards at the top. So I assumed my shear flow was positive going that way. The net result of the calculation demonstrates that it's actually going to be the opposite direction in terms of its magnitude. But no matter, it's just a sign convention and we know what it means now. Okay, so we have potentially a couple of sanity checks that we should do. Anybody want to suggest some?
Q1 and Q3 should cancel out because they're equal.
Yeah, so great observation. So one of the things that we know was that there was no SY, right? Or I'm sorry, SX, right? So we said that SX was equal to 0. That was by our problem statement. So the sum of all forces in X has to be equal to 0. The magnitude of Q1 and Q3, it was equal in magnitude, although the arrows were pointing left on the top and right on the bottom. So equal in magnitude, given those arrows, they actually do cancel each other out. So we're happy about that. Some of the forces in the X direction works out pretty easily. A natural second sanity check would be that the sum of the forces in the Y direction would be equal to the applied load. So of course we assumed an applied load of SY. And if we look at what we calculate for Q2, we're saying the shear flow is equal to minus SY over 2H. Now keep in mind, what is the definition of shear flow? It's shear stress times thickness. So to confuse, and it has units of force per unit length. So if we want to convert that into a force, we multiply by a length. In this case, the calculated length is 2H. Okay, so 2H is the length times the magnitude Q2 should give us the total shear stress, shear load, shear force is what I really mean to say, in the vertical direction. And if we look at what the magnitude, so if we multiply this by Q2, multiply this term by 2H, so the 2H then cancels. Keeping in mind that our assumed direction of Q2 was down as our diagram had it. And of course, our SY was up, and the minus sign here confirms that the two are equal. So there's a couple of good sanity checks on the calculated outcome. Now again, these are not exact. If you went in and did a finite element model of this, you would find that it did vary a little bit from this calculation, but it is a conservative calculation. These magnitudes are slightly higher than what you would get if you did a much more detailed calculation. So being on the conservative side is obviously what engineers tend to want to do because it's safer. It also is really quite easy to do these calculations, as you can see. They can be done by hand. The things like the Boeing 747 were designed on these principles and have been flying for, well, that was designed I think in the 60s, if I'm remembering correctly. So it's been flying for 60 years without structural problems using these theories. Okay, any more questions on that particular type of content?
I have a question.
Okay.
Why did you subtract the area A2 minus A2 when evaluating the shear flow 3?
Yeah, so, okay, good question. Let me get back to it. Remember, it is the area times the y position. So it's our y position measured from the centroidal location. So both of these areas, A1 and A2, were in a positive h, positive y magnitude h. A3 was now in a minus h magnitude a. Okay, so that's why we subtracted A3. I brought that sign into the calculation right here. I'm not sure who asked that question, but are you with me then?
Yes, thank you.
Great. Okay, any other questions? All right, hearing none, we're going to move on. I feel like there's all these little intricacies that we need to learn with these calculations, and once you get the hang of them, you realize that in general they're not very hard to accomplish. But of course, it's a lot of things to remember as you're seeing it for the first time. So if you remember from last lecture, we were doing multicellular structures like this, wing cross section. Okay, we did those. That was all thin-walled stuff. We did not have any structural reinforcements in the calculations we did at that time. But now let's assume that this is a real aircraft wing, so maybe it actually has a spar cap that is a non-trivial concentrated area at the spar. Something like this is actually pretty realistic. Although my art is getting worse as time passes here. So now we need to understand what are the implications of these point areas, we'll call them, area reinforcements, on this idea of shear flow continuity as we come into a junction. Okay, so our previous statement was that the sum of all flows into a junction has to be equal to 0. So here in this particular diagram, Q1 is out, Q2 and Q3 are in. So if we said Q2 plus Q3 minus Q1 is equal to 0, we could then solve that for Q3 and we'd get this equation. Now, what we saw in the lecture up to this point today was that when we cross these areas, something happens. Something happens. So we got to think about what that really means. So here instead is just a schematic view of that same structure, but now we've got an area reinforcement. Okay, so if we go back to this beam that I just drew, I'm taking a differential length in the z direction, and I'm kind of cutting out a differential element that captures the entire area and then has a distance delta z. And I'm applying equilibrium to that structure, and that is what we have here. So there's a dz right here. Okay, so what do we know? Well, we know a bunch, right? So we know, of course, that the sum of the forces in the z direction has to be equal to 0. we know that due to bending, we have to assume that it's possible that the stress due to bending, sigma ZZ, changes here relative to here. So across some delta Z distance, we're going to have a change of stress delta sigma ZZ. So if we, so if I say here on the backside, let me just draw, I'm going to try and draw just this cross-sectional area, okay? So this is the two ends. On this side over here, we've got sigma ZZ. As we move in the positive Z direction, we have sigma ZZ plus delta sigma ZZ. Okay, so on the front face, in the positive direction, the stress magnitude is sigma ZZ plus delta sigma ZZ. We multiply that times the area to get the force contribution on the front face there. The force contribution on the back face is sigma ZZ times that area. We still have several components that are now contributing to the Z force. We've got a shear flow Q3 up here. We've got a shear flow Q1 down here, and we've got a shear flow Q2 over here. So we're going to capture all of those, and we need to, of course, recognize the direction of the arrows in each of these cases. So Q1 is in the positive direction. Let me see here. I got to make sure. Here's Q2 here, and that one's in the negative direction, and Q3 is also in the negative direction there. So Q2 and Q3 are each negative. Q1 is positive. So the sum of all of these forces has to be equal to 0. So these shear flows times the differential length dz, that gives us force, and that's the sum. And then, of course, we're going to recognize, much like we have throughout the semester, that we can take the limit. First of all, we can divide by dz, and then take the limit as dz goes to 0. And when we do that, we get this equation. Q1 is equal to Q2 plus Q3 minus the area times d sigma zz dz. Okay, so now Nicole's asking a question in the chat window. She's asking, are the arrows that don't have Q's next to them stresses? So this one is sigma zz stress. On the near side, sigma zz plus delta sigma zz. On the back side, just sigma zz. This Q2 really applies for here and here. And again, you're thinking of this, remember what we do with shear. So, it's the magnitude is the same on the two sides of the corner, and the arrow points in, sort of either towards each other or away from each other, depending on where you are. So here, Q2, they're both pointing away. So the magnitude is equal across as we go around that corner. So Q2 applies to both those arrows, and Q1 applies to both these arrows. And of course, this is just the length scale delta sigma zz. David asked which one is just sigma zz. So that would be this one over here if we're saying that this is the positive direction for z. Okay, so anyway, this is the equation we've derived. Of course, we still need to think about what that, here we have this critical part of the equation now that wasn't there previously. That is the A times d sigma zz dz. And of course, sigma zz itself comes from bending in the beam. So if we had an Sy that existed and we had a corresponding Mx, we'd have the magnitude of stress was Mxy over I. And the derivative of that mx with respect to z is equal to sy. So these are beam bending equations derived earlier. And of course, y in this case is the position of the stringer. because in this calculation, it is the stress of this stress of the stringer itself. So this now references the y position of that stringer. And we bump all that stuff into the equation here. That's this equation. Okay, and what we get is that this equation now is slightly modified but represents the same things. Now, Q1 is equal to Q2 plus Q3 minus the resultant shear on the cross section times the area times the y position over the I value. Okay, so we've reached the end of our rather lengthy, weeks-long excursion into beam theory. Kind of all of that we've covered in these weeks would be described as beam theory generally, or you might actually separate them into beam bending and then torsion theories. These are if you wanted to be more specific, I sort of in my mind think that beam theory encompasses all of that. But if you are talking about a specific problem, you may be referencing just beam bending or just axial torsion or a combination of them. I hope that you see that this is an extremely valuable tool for aerospace engineering, because all of these aerostructures almost all of the aerostructures that we deal with on sort of a global basis, the fuselage, the landing gear, the wing, the tail, even some of the control surfaces are very well describable by these beam-like properties. So these are extremely useful derivations and equations and methods that we're using. Now, I still have to be cautious because we did make a number of assumptions along the way. For example, the length of the beam is much longer than any length in its characteristic cross section. We talked about thin-walled sections. We talked about many assumptions, geometric and material assumptions along the way. That may not always be true, and so there are some more advanced beam theories that can be examined and talked about when those assumptions that we made are not as precise as we'd like them to be. But that stuff will be covered in other courses if you continue on for a graduate degree in structural mechanics, aerospace engineering here at WMU or elsewhere. But with respect to what you need to know as an engineer going out into the workforce, I think you have a pretty good foundation now for understanding how aerostructures are designed. Okay, now we're going to close the door on that section for now, except for maybe another homework set. And we're going to then enter into this new segment of the class. That is this idea of energy methods and approximate solutions. So within the bounds of the assumptions that we made, the calculations we did in what I'm calling section 2 of the course are correct. I hesitate to say exact, but they are correct. Okay. We've kind of put some caveats on some of those and talked about, well, where is it not exactly correct? But within the assumptions, they're correct. Now, we still would like to have methods for solving problems that are a little bit more complex than we have. And we also recognize we don't always need to be exact, or we don't need to be precisely correct. We're engineers, most of the time we're building in a little bit of a safety margin. And so can we come up with methodologies for analyzing even more complex structures and getting an engineering solution, a good enough solution? And so that takes us into the domain of energy methods and approximate solutions. So that's what's going to be left for the, I think we have about 4 lectures left in this class after today. So we're going to spend those 4 lectures on these energy methods and approximate solutions. Now, of course, in order to understand energy methods, you have to understand energy. And you guys have gotten a pretty good exposure to energy already. You certainly have talked about it in your physics courses. You may have talked about it in some of your other mechanics courses. We've talked a fair amount about potential and kinetic energy in a number of the courses that you've gone through so far. For the next little bit, we're going to sort of review some concepts of energy, and we're going to then apply some of these concepts within this discipline of elasticity and structural mechanics in ways that you probably haven't encountered before. So the first concept that I want to introduce you to again, or just review, I should say, because you've seen it before, is the concept of work. Note that what we're going to be talking about right now assumes conservative forces, okay, and that's a caveat. When we have dissipative scenarios in our engineering systems, then some of the energy conserving assumptions that we're going to make over the next several lectures need to be modified. But for the time being, let's assume that we have a conservative force. So there's an energy preserving principle at work here. Now, keep in mind, we have forces and we have moments. Forces, of course, cause linear translations. Moment, of course, cause angular translations or angular motions. The linear displacements are coupled to linear forces. The component of force in the direction of displacement contributes work. And so you have recognized in the past that a term work is equal to the force dotted with the displacement. Force and displacement are both vectors, and their dot product then becomes a scalar magnitude that we've called work. Now, of course, recognizing that angular moment and angular rotation are very much analogous to the idea of a linear force and linear translation, we can just go ahead and state without much derivation that another measure of work is moment dotted with angular rotation. And so when we express it this way, we recognize that moments and angles are vector quantities. Okay. Now we have to be really careful when we say that angular displacements are vector quantities. So just jot down in your notes the caveat here that this is true, that it is conservative, and it is it acts like a vector when the angular rotations are relatively small. When you get larger angular rotations, then you're not going to find that it behaves like a vector anymore. What do I mean by that? Well, one of the principles of vectors is that we have components and that you sum them together. Okay, so this vector is equal to this plus this. Now, and I encourage you to do it, you can do it with your phone as you're sitting at your desk. Most of us have our phones in front of you. Think about if I twist it once this way around the x-axis and then once this way around the y-axis, what's its orientation going to be? Okay, then take it back to its original and go about the y-axis first, and then rotate about the x, and you're going to find that it is no longer conservative in its its orientation. So when you have large angular deflections, you need to recognize it does not transform like a vector anymore, but for relatively small angular rotations, it does transform like a vector. That means that you could add the two rotations together and get functionally the same outcome for small angles. Okay, so it's, and these are things I don't need to dwell on them for too much time. Only the component of force or moment in the direction of that motion actually contributes work. It is a dot product. And I mentioned this already, work is a scalar. So if we wanted to lay out in a little bit more detail what these equations are, so I said work is equal to force dotted with displacement. Of course, force has components Fxi plus Fyj plus Fzk. Displacement has components dxi plus dyj plus dzk. And so the magnitude of the work, which is a scalar, is equal to Fx, it's Fxi dot dxi. The dot product of I dot I is 1. So we get Fx dx, we get Fy dy, we get Fz dz. Of course, you could, when you're thinking of the dot product, Fx dotted with dj, dyj, I dot j is 0, so that goes away. J dot k is 0, and so forth. So anyway, dot product Fx dx plus Fy dy plus Fz dz, and that is how we express the magnitude of work due to forces. Only the component of force in the direction of motion does work, and of course moments are identical in that sense for these small angles. Now, you guys have heard of the word potential before. I don't know how much thought you've put into it. You probably just accepted it without a lot of thought, at least if you were at all like I was at many points during my earliest undergraduate days. The idea, oh, potential energy, okay, so that's what it is, great. I think I understand it. But the word potential actually has a somewhat more mathematical meaning that maybe we weren't as attuned to the first few times we were introduced to these concepts of potential energy and similar. And that is that we can define a potential function. This is a general mathematical description now. A potential function is a function for which there is a generalized force that is the derivative of some potential function with respect to a given direction. So this is sort of what defines what a potential function is, where in this case the potential function is actually v. You take its derivative with respect to a given direction and it gives you a force. So expanding that out, by the way, this is a notational scheme where I can vary from 1 to 3, or that's meaning x, y, and z. So the force in the x direction is minus the derivative dv dx. F in the y direction is minus the derivative dv dy, and f in the z direction is equal to minus dv dz. So this is what a potential equation, or v is the potential function, and the generalized set of forces that fall out when you do the derivatives are come from this definition of a potential function in a conservative field, a non-dissipative field. Now, I've said you guys are already familiar with this. You're well along in your engineering careers. Certainly, if you've gotten to this point, you've understood most of this quite well to this point. So here's a potential field that you are well familiar with, and that is the gravitational potential. We know that as we move a mass up or down, we describe it as changing its potential energy. When you climb up on a ladder, you have potential energy that then gets turned into kinetic energy as you fall off the roof, right? So that's the idea. So what is the potential? We need to come up with a mathematical function that describes this scenario. So what is the potential function? Well, it's pretty straightforward. You've seen it before. Here I'm going to say that V, the potential, is equal to minus mgy plus c. C is just a constant in this case. Mgy, you can think of this as being mass times gravity times the height. Now we have the minus sign in front of there to make everything quite convenient, and keeping in mind that this is a description of a mathematical relationship, really. So dv dy has to be equal to a minus of a force. So this is where we get force is equal to mass times gravity from with respect to gravitational fields. Okay, note that this is very much a sort of a structural mechanics view of it. We're using gravity as a potential example, but you've heard of potential in other contexts before. I don't know if you've heard the word voltage before, and think of the potential associated with voltage. There's similar potentials in our related disciplines, electronics, fluid mechanics, thermodynamics, etc. Thermodynamics actually gets a little hairy because there's that sort of dissipative concept in thermodynamics called entropy that works against us. Anyway, so here again, if we have a displacement increment, differential displacement ds is going to have components dx, dy, and dz in the three directions I, j, and k. And the work increment done by a force is, and you've seen this on the prior slides, but the reason why we're emphasizing this as being slightly different is that we're talking about displacement increments now. So when we have a small increment of displacement, we get an increment of work. And that is, rather straightforward here in saying that it's the fx component in the dx direction plus the fy component in the dy direction plus the fz component in the dz. And really, these should be subscripted. I don't know why they're not. I'll try and remember to fix that next time. Now, so that is a differential contribution of work, dW, due to a differential increment of displacement in a force field. Now, going back to this idea of potential and the relationship between potential and force, I can replace this force with the potential function. So here we have dW, the differential work, is equal to minus the derivative of the potential field with respect to x times dx plus, I should say, minus the derivative of the potential field dy times dy minus the derivative of the potential field dz dz. And so what we see here is that this is a generalized form of a derivative. And so here's our expression that is actually quite meaningful. An increment of work occurs when you have an incremental change in potential. And these two are opposite of each other in sign. And what we can say then is if we sum the two of these things together, work plus potential, we're going to get 0. This is a conservative principle. This is the principle that if you do work, if you move that mass up in carry it up to the top of the mountain, you've imparted some energy to it by doing work, and you can recover that energy as you bring it back down off the mountain. Any questions? You guys are pretty quiet at the moment. All right, can you confirm? Can somebody just confirm that you can still hear me? All right, thanks, Gavin. Okay, so here we go. So let me give you just a few more thoughts on this idea of a potential equation, a conservative potential expressed this way, dW plus dV is equal to 0. In a closed conservative system, that is a system without dissipation, the potential change, and this you'll see it in different places written in different ways, dV, delta V, the All right, ladies and gentlemen, computer 2 is still online. For some reason, computer 1 is not being broadcast to you. Can you see it now or no? I'm seeing some thumbs up. Okay, you were just saying, yeah, you heard me. All right. Yeah, my computer's actually quite warm too. I wonder what's going on there. All right, I just gave it a hard reboot because it froze up. It's going to take me, on the order of a minute to get those slides back up on screen for you, maybe a little bit longer. So let's take the opportunity to ask questions if you have any. By the way, the AIAA hosted kind of a neat event the other night. I want to say thank you to those people who were there and who made that possible and who did all the work prepping it. It was really cool. All right, should be coming in here in a moment. All right, I'm back. Oh. Okay, testing. Now I'm getting a major echo. Test 1, 2, 3. Testing. Okay, so it's let's see here, 3:40. So we have about 10 minutes left. Sorry about that technical glitch. I guess it happens every once in a while. Okay, so what we've described now is this idea of potential, and another concept you are familiar with is the concept of work. And we've already introduced work, of course, this time around. Now, you can imagine a scenario where we have a structure. In this case, I don't know how well you can see this image over here on the left, but I've got a vertical column that I'm pulling vertically with a point force P. And it has, at that point, this is an elastic structure, so it deforms, and we're going to say that it deforms a certain magnitude y. Now, this often is, but does not need to be linear, so I'm drawing a graph here that actually accepts that it doesn't have to be linear. So here we've got this curve that sweeps out a what amounts to a spring response for the structure. So it is nonlinear. Now the total work done by the force P, you recognize, is going to be equal to P, the magnitude of that force, times the displacement. And it also can be expressed in this way. So the integral is or I should say the work done is the integral from 0 to the distance y of the constant force P times dy. I have to be a little careful. It's made the mistake here. In this case, P is not constant. It depends on how far you've pulled it, right? So we need, I misspoke. It is not a constant force. It's obviously now a function of the displacement. So the total work is equal to the integral of the force at every increment integrated through the increments from 0 to y. Now we can flip-flop these two axes, and I can put y on the bottom axis, and I can put p on the top axis, and I can, again, express this curve. And now we see work as being an integral under the curve. So it amounts to an area under the curve of the response of p versus y. So that is work. And by the way, this work is being done on this surface that is moving. That is work being done on the surface that is moving at the application of the point force. So of course we need to recognize that that energy needs to be conserved. It needs to go somewhere. We know that these conservation principles are true, at least in a non-dissipative conservative system. So what happens to that energy that comes associated with that work? And so really here's what happens. The force that is transmitted, the force at the tip gets transmitted into the bar. That bar, the force carried now by the bar, causes deformation, i.e. called strain in the bar. And then it gets stored as a type of energy in the bar. And you guys have seen these things many times. You've heard of a spring, which stores energy. You think about things like a diving board, which allows you to store energy, to allow you to bounce and jump high. Crossbows that store energy to allow you to, fling arrows at high rates of speed. All of those things are storing energy in strain. So now we need to come up with a way of describing the energy associated with strain. Here I've got a simplistic uniaxial bar structure. We're going to say it's uniform. It has a cross-section A, it has a material modulus E, it has an overall length L, and it's pulled with equal and opposite forces P. So in general, we can have a stress-strain curve. It does not have to be linear. I'm drawing a more general stress-strain curve here. Although, of course, it could be linear, in which case we would actually call that magnitude E of the slope. The slope is of magnitude E. But in general, we have the same concept of the area under the curve now is a measure of energy stored through strain. So we're going to define this term called the recoverable internal energy, or perhaps more abbreviated, the strain energy. It is the integral under this stress-strain curve. So it's the integral of stress d-strain. Now keep in mind, stress and strain are point-wise quantities. They vary spatially. Not every position in the structure is going to have the same stress and strain. Nevertheless, the amount of work done on the outside is a finite quantity. We need to sum up all the strain energies internally. So when we say that this is an internal strain energy, we actually need to think of this as a volumetric density of strain energy. And so the total strain energy is the integral of the strain energy density U0. Used to live, I should say my parents used to live next to the University of Wisconsin, so I think a lot about UW sometimes. Anyway, U sub 0, this is the strain energy density per volume. You integrate that over the volume and you get the total strain energy stored in the structure. Okay, so for this particular uniaxial bar, no, that was this one here. Right? And I said it has uniformity to it, so it has uniform material properties, cross-sectional area, and length. So the strain energy density is at every point is going to be the same because it's the same material response and the same strain. And so in this case, the strain energy density being a single value, we just multiply that by the volume AL to get the total strain energy. So the term that you need to know here, really two of them. One is the strain energy in total, and then there's the specific strain energy or the strain energy density or the strain energy per unit volume. Any of those are reasonable descriptions of the same thing. Most concisely, it's probably strain energy density is the term that's used most frequently. Let's apply that concept to a linear elastic material. What does linear elastic mean? Well, it's pretty straightforward, right? It's linear, that's the point. So here we have a linear response. Again, now we're looking at the area under this curve is the strain energy density. So if we express sigma is equal to E times epsilon, it's linear. We then express U0 strain energy density is the integral from 0 to strain of E times epsilon. That's stress destrained, E epsilon destrained. We then recognize, of course, the integral of epsilon d epsilon is epsilon squared over 2. So the strain energy density is 1/2 E epsilon squared. We can, if we so choose, do substitutions to express this in some other ways. So equivalent statement, U0 is 1/2 sigma squared over E, or 1/2 sigma E. These are all equivalent statements of strain energy density, either one of which may be used at a given point, depending on what's most convenient. So for elastic materials, the work due to external loads is stored as energy in the bar. This is kind of like a summative statement of all this stuff. Now we talk about linear elastic. That's what most of our structural work in this class is, linear elastic E epsilon. But there's nothing to say that you can't have nonlinear elastic. So this one would be nonlinear elastic. Obviously nonlinear and curve. Elastic, what that word means, just for clarity, is that if you unload along the same path. That is a conserving principle. If you are in an elastic system, you go up and down the same path. If you get into a plastic zone, if you have plasticity, then you unload along a different path, and actually energy is consumed in doing damage to the material. And that is going to be an irrecoverable energy. So we're not going to talk about that much for the time being. That's the domain of a future lecture, perhaps in a future course. But for an elastic material, the key is that it unloads along the same path, and so all the energy is recoverable in an elastic material. Okay, I think that's a good place to stop. We're at our formal stop time. In fact, we're a couple minutes past. So I'll hang out here for a few more minutes to take any questions you may have. Otherwise, have a wonderful Thanksgiving break. I know I need it. I'm sure you need it as well. As my understanding is that the remote computer labs will be open for all of Thanksgiving break. So, take some time to continue working on your projects if you so desire. I hope to talk to you guys soon after you have a good rest. Don't forget the homework set is due tomorrow. I see there are a couple of questions here. Let me go ahead and address those. So Ron asks, I don't think we were on this slide when you froze. I'm sorry, I guess, did I miss a slide? I'll go back to whatever slide you think I missed. This is where I thought we dropped off.
No, I think it was the slide before. Yeah, it was that one.
Yeah, so these are not terribly profound thoughts. Basically this is just recognize that conservative systems exist where there's no dissipation. And in that circumstance, work and some sort of potential. What does this really mean? This means that internal strain energy has potential to do more work is what you should be thinking about there. I'll leave this slide up. Ethan says we were a slide or two back. Ron says, so would P be like a spring force? Yeah, absolutely. In this example, we're storing energy in the structure as it's deforming. And so that structure is acting like a spring. It is a recoverable energy that you can use to actually do work. And that's what a bow and arrow is. You're deforming a structure to store energy and then recovering it, and turning it into a different form of energy. Okay, so I see Ethan's highlighting Nicole's question that maybe I missed. So Nicole's question was no dissipation and concern. Let me go back and look at the exact question. Can you explain what you mean by no dissipation for a conservative system? It's probably easier to actually describe what I mean by dissipation. So dissipation occurs that some of the energy that's in the system gets lost to something else that you cannot recover it. An example of that might be friction. If you are, I happen at this moment to have my phone on my table, right? If I push that phone from left to right on the table, as I'm moving it, of course, I'm doing work. But then when I stop pushing it, it stays where it was pushed to. It does not have any stored energy to return to its prior location. Why? Because friction dissipated energy. Friction dissipated the work that was going on. And so it's, depending on what you're calling the bounds of your system, you might say, well, that has created a thermal energy. And you might track thermal energy and still say that energy is conserved, but that is no longer recoverable work from the perspective of structural mechanics. So, dissipative systems, anything that provides viscous dissipation, if you're moving a structure through a fluid and that fluid then dissipates some of the energy that's not available to do work. What other example? The materials themselves can have some sort of dissipative property to them. If you think about if you were to pluck a guitar string, what's going on is it vibrates, and over time, energy is dissipated. It's not all dissipated quickly. It takes some time for that energy to be dissipated. Some of it is lost as viscous dissipation into the air, as it's vibrating and pushing air out of the way. And some of it is lost to changing the temperature of the guitar string itself. This is an internal dissipative activity. So even if you pluck that guitar string in space, well, first of all, you wouldn't hear it, but it would still vibrate, but it would not vibrate indefinitely. It would dissipate energy as well. So in life, there really are no perfectly conservative systems, although we typically we make an assumption that it's going to be conservative over a small time frame.